All right, so let's get started. So the next homework is online now. It's due on Tuesday again. Okay, so it's coming Tuesday, and then exam 3 will be after the break. For in-seat classroom disinfection, I'm asking Josh and Cassandra. Okay. All right, so I think we can finish chapter 23 today, and then I'm not sure if we get a chance to take a look on the next chapter, but I put them on here as well. So just we'll just go and see about that. All right. So let's take a look on what we checked last time. So last time we took a look on the elements, electrical elements in the AC circuit. So for a resistor in an AC circuit, so it's pretty much the same as it is in a DC circuit. Okay, it responds to the voltage applied to it right away. So if voltage is changing as a sine function, then your current is also changing as a sine function. Okay, so that means you'll expect a peak value for the voltage on it, and then also current on the resistor as well. So the current and the voltage, they are in in phase. That means they peak at the same time. They will have minimum at the same time. And to calculate the power consumed by a resistor in a AC circuit, you can do I squared times R, but this time you will have to do the Riemann. You have to use the Riemann square quantity. Okay, so you use Riemann square quantity for the power here, gives you I Riemann square times R. And then you can also calculate with V square over R. Again, V, you should be using the Riemann square. Okay, R is constant; it doesn't change. So you still have R there. Or you can do the power equal to V times I, the current times the voltage, or voltage times the current. Again, you'll be using Riemann square quantities here. So you're doing VRMS and then IRMS. Okay, multiply them together. If you have an inductor in the AC circuit, then this time the current doesn't respond to the voltage right away. It has a lagging effect. So current will peak after the voltage has peaked. Okay, so that's by 90 degree or pi over 2. So your current is lagging the voltage in that sense. However, it still has response. So then we can come up with this version of Ohm's law for an inductor. So we call its reactions to the voltage as a reactance. So it's called inductive reactance because it's an inductor. We use X for the symbol for reactance. Sub L means it's an inductor. It's equal to 2 pi F times L. Okay, F is the frequency of your AC voltage, L is the inductance. Then the current is equal to V divided by XL. Okay, so similar to Ohm's law, I equal to V over R. Okay, so X is analog to R in this case. You can also write XL as omega times L, where omega is the angular frequency equal to 2 pi times F. Okay. All right. In that case, because your current is lagging the voltage, so then it's a different, slightly different sine function. So it's lagging by pi over 2 or 90 degree. Okay, so you have minus pi over 2 here in the sine function. All right, and then this is equivalent to a cosine of omega t. Okay, sine of omega t minus 90 degree or pi over 2 is equivalent to a cosine omega t. To calculate the electric power consumed by inducting AC circuit, you can do again. You can start with the voltage on it and then times the I. Okay, it turns out to be a sine of 2 omega with multiplied by constant terms here. So if you do average of this whole thing here, it will give you 0 because sine function, if you do average, is 0 because half of the time sine is above 0 and then the other half of time sine is below 0. Okay. So that tells you the inductor in an AC circuit does not consume any power. Okay, it actually simply store the energy in the inductor. On the other hand, a capacitor, so in this case, the current of a capacitor inside an AC circuit actually is leading the voltage, so by 90 degree in that case. Okay, so then sine of, you will get a current as a sine of function omega t plus pi over 2. Okay, in that case. And we can describe the reaction as a capacitive reactance. We use Xc here equals to, now in this case it's 1 over 2 pi f times c. Okay, in the previous case for inductor is 2 pi f times L. This case is inverse of 2 pi f times c. And the current then can be calculated similar to Ohm's law as V divided by the Xc. Okay, or Xc can be written as 1 over omega c. Omega again is 2 pi times f. Similarly, you can calculate the power consumed by a capacitor in the AC circuit. It turns out to be also a sine function, and then so the average of sine function again will be 0. So for a capacitor in an AC circuit, it does not consume any power. It simply store energy. Okay. And we also take a look on if you have a combination of all those three elements in a AC circuit, so then we can call the collective reactions to the AC voltage as impedance in that case, Z. So then I is equal to V divided by Z. So if you have maximum peak value I0, then it will be equal to peak value in V divided by Z. If you are looking for the root mean square quantity of current, that will be equal to the V root mean square divided by the Z, the impedance. Okay. And the impedance, we took a look at it last time. It turns out to be equal to, the Z is equal to square root of R squared plus the inductive reactance minus the capacitive reactance, and then squared it. Okay. And it should also have the dimension of ohms, the SI unit of ohms. Okay. All right, and then we were about to check on this example last time. So this one says find the root mean square voltage across each element in an RLC circuit with R equal to 8.8 kilo ohm, C equal to 0.12 microfarad, and L equal to 28 millihenry. The generator supplies an RMS voltage of 115 volts at frequency of 60 hertz. Okay, so we are looking for the VRMS across each of the elements here in this case. So we can take a look here. So you have a RLC circuit. You can draw the figure here, RLC. So this is R, this is L, this is C. And then this is the, actually I should just draw it as a circle with this sign here. That means this is an AC voltage, AC power supply. Okay, so battery is a DC supply. That's not the correct power source there. So it tells you this guy VRMS is equal to 115 volts. So what would be the VRMS on the resistor? And then you're looking for VRMS on the inductor, also the VRMS on the capacitor. Okay. So to find those quantities, the first thing you need to calculate is what will be the current in the circuit, because they are in series. So then you can figure out what's your I. RMS first, okay? And then once you get that, VRMS of this guy will be just I times that. For VRMS of this guy will be equal to the I times XL. Okay, you can calculate what's XL. And then on this guy will be the current RMS times XC. Okay, so that way you can calculate them out. To figure out what's the IRMS, you'll be doing IRMS equals to VRMS divided by the impedance of the whole circuit. Okay, so so it looks like we have to calculate the impedance. Okay, so Z for the impedance is square root of R squared plus XL minus XC squared. Okay, we have R. We can also calculate XL, XC because we are given the inductance and then the capacitors, the capacitance of the capacitor. Okay, we can do that. So let's calculate those first. XL is equal to 2 pi F times L. So 2 pi times 60 Hertz times the inductance is given as 28 millihenry. So minus 3 Henry. Okay. So that gives you 10.56 ohms for your inductive reactance, XL. You can also calculate your XC, reactive, the capacitive reactance. So that's slightly different formula. It's 2 pi F in the denominator, okay? So remember, those two are different formulas. You'll be doing 1 over 2 pi 60 Hertz, and then the 0.12 microfarad, okay, minus 10 to the 6. So your XC is equal to 22,105 ohms, 22,105 ohms, okay? Once you have those two, you can calculate your Z, the impedance. So the resistance is given as 8.8. That's in kilo ohms. Okay. So times 10 to the third plus you'll do this guy minus XC and then square it. All right. So that gives you your impedance to be equal to the 23,782 ohms. Okay, that's my impedance. Once we have the impedance, we can calculate what's the root mean square current in the circuit. Okay, so you can do that now. It's equal to the root mean square voltage 115 divided by 23,782 ohms. So that will give you 4.836 times 10 to the minus 3 in amps. All right, that's your root mean square current in the circuit. After that, you can calculate what would be the root mean square voltage on the resistor. So root mean square voltage on the resistor should be equal to the root mean square current times the resistance. Okay, so it's this number times 8.8 kilo ohms. That would be equal to 42.6 volts. Okay, that's for your resistor. For your inductor, that should be the root mean square current times the XL, the reactance. 4.836 times 10 to the minus 3 amps times this guy 10.56 ohms. That will be 0.0511 volts. Okay, this is on your inductor. Oops, it's not in the camera range. Okay, so for the RMS voltage on the reactant, the inductor is the root mean square current times the reactance. Okay, similarly for capacitor is the root mean square current times the reactance of the capacitor. So this is 4.836 times 10 to the minus 3 amps times XC is 22,105 ohms. That gives you 107 volts. Okay, so this is on the your capacitor. All right. Now you have the voltage asked. Okay. The last step I would do is I will verify the results. Okay. So because for root mean square quantities on each one, the voltage, if you do VRMS on the R plus VRMS on the L minus VRMS on the C, that should be equal to the root mean square quantity voltage of 115. Okay, so should be equal to 115 volts. You can double check on your number here. The first one is 42.6 volts into square plus the second one 0.0511 minus 107. Those are in volts square. Okay. And it turns out to be exactly 115 volts. Okay, so you have that. Just double checking, right? Now, because you have RLC circuit, so just keep in mind that your root mean square voltages, they do not add up algebraically, okay? You do not just simply add those up, because if you add those up, it will not be equal to 15, okay? This is the correct formula for that. Because the L and C, they are not in phase with the current. So that means when this guy has a peak voltage, this guy is not having a peak voltage. This guy is not having a peak voltage either, okay? So you cannot simply just add their root mean square quantity up or their maximum value up for that. Instead, you have to do the voltage on the resistor square plus the voltage difference on the inductor and capacitor square, okay? That should be equal to your overall total voltage, okay? Because there's a phase difference there. They don't peak at the same time. All right. Any questions you guys might have on this one here? All right. So if you guys are clear, we will move on. Now, for the impedance in RLC circuit, we see that Z is equal to square root of R squared plus XL minus XC squared, right? Now, there's exception here that when XL might be equal to XC, because XL is a function of frequency, XC is also a function of frequency. So if you can have those two equal to each other, then in the denominator over here, because it's R squared, that's constant, okay? That doesn't change with your frequency. The resistance will not vary with frequency, but those two reactants, they vary with frequency. So you can tune your frequency so that these two are equal to each other. In that case, then you'll have minimum value of your denominator as R, and then you'll get a maximum current, okay? So this is what you would have. So then if XL equal to XC, you'll have maximum current of RMS. In that case, XL is equal to 2 pi frequency times L, and then XC is equal to 1 over 2 pi F times C. And then when that happens, we just say this is F0. This is the resonance frequency because that will give you maximum current. Okay, so you can set this up. You can solve for your resonance frequency of an RLC circuit. It turns out to be 1 over 2 pi square root of L times C. Okay, that's your resonance frequency for an RLC circuit. So when you reach the resonance frequency, then your current will be maximum. So your current is a plot like this. So this is for a small resistance. This is for a larger resistance. But either way, you will get maximum current RMS when the F equal to F0, which is the resonance frequency. Okay. And that's pretty much how the radio station is working. The radio station will give out a certain frequency, and then in your radio, you'll turn your radio to that frequency. Okay, so your radio will have an RLC circuit in it. So when you can tune your frequency to that frequency, then you'll get resonance effect that will give you clear signal of radio. Okay, so it says in this problem, it says to receive AM radio, you want an RLC circuit that can be made to resonate at any frequency between 500 and 1650 kilohertz. This is accomplished with a fixed inductor 1.00 microhenry connect to a variable capacitor. All right, so you can change capacitor value. What range of capacitance is needed here in this case? All right, so we know that the resonance frequency is equal to 1 over 2 pi square root of inductance times the capacitor. It says L is fixed. This is fixed as 1.0 times 10 to the minus 6 Henry, microhenry, okay? And then your C can vary. It can go from minimum number to a maximum number, right? So it's asking you what's that minimum and then what's that maximum, right? You want to have your resonance frequency to cover the whole range of the AM frequency range, right? So for the frequency range, it says from 500 kilohertz to 1650 kilohertz, right? So basically, then this is what you would have. So you'll replace your F0 with that guy, right? And then this is on over here, this is 500 times 10 to the third hertz. Less or equal to 1 over 2 pi square root of L times C, less or equal to 1650 times 10 to the third hertz, okay? You can multiply each term by 2 pi. So 2 pi on this one, 2 pi on this one, and then 2 pi on this one, okay? So that's the holds there. So you can see this one and that one will cancel out, okay? And then you will have square root of LC. Now this is a positive number, this is a positive number. So you can square every term here you have, okay? So let's do this. 2 pi times 500 times 10 to the third hertz. You can square that one. Should be less or equal to 1 over LC. You get rid of your square root. less or equal to 2 pi times 1650 times 10 to the third hertz. Okay. All right. And then you can multiply everything by L because L is the known number. Okay, you know L. L is 1.0 times 10 to the minus 6. So multiply this by L, this by L here, and then this guy by L. Okay, you'll get rid of L. So then you will have L, you can put the numbers in now, 1.6, 1.0 times 10 to the negative 6, 2 pi times 500 times 10 to the third hertz square, less or equal to 1 over C, less or equal to 1.0 times 10 to the negative 6 Henry times 2 pi times 1650 times 10 to the third hertz. Okay, and then square it. All right. Now you don't you want to find the range of C, but this is 1 over C, so you can do inverse of that. All right. Now this is a little bit tricky. When you do inverse of a term here, if you do this one inverse, that will give you, if you do inverse of that, then you'll be doing inverse of this, inverse of that, right? But the sign here or the direction here will change, right? If you do inverse, okay? So for example, if you got 2 less than 3 less than 4, right? But if you do inverse of it, then 1/2 should be greater than 1/3, greater than 1/4, right? So if you do inverse operation, then the direction of the that will change. Greater becomes less, less becomes greater. Okay, so that's what you get. So at the end, you'll get all this together 1.6, 1.0 times 10 to the minus 6 Henry, and then 2 pi times 500 times 10 to the third hertz square inverse less or greater or equal to C, and then greater or equal to this whole thing. Inverse. Okay. So that will give you at the end, on this one, it's going to be 0.1, roughly 101 farad, greater or equal to C and greater or equal to this end is will be 9.3 times 10 to the negative 9 farad. Okay, so this is your minimum. This is your maximum. Okay, so you should have a capacitor that can vary from here to that number. Okay, a range of that. All right. Any questions you guys might have? Okay. So if you are clear, we can then take a look on the power of an RLC circuit. Okay, so in an RLC circuit, you can calculate the power. You can use either I squared times R or V squared over R, or the V times I. Okay, in this case, again, because this is an AC circuit, so you want to use the root mean square quantities. Okay, so for the current and then for the voltage as well. We learned last time that for an inductor in an AC circuit, it doesn't consume any power. Okay, And then also for a capacitor in your AC circuit, it doesn't consume any power either. So then the only element that will consume power will be the resistor. Okay, so then the power for a RLC circuit will be just the power of the resistor, which is equal to I squared times R. You take I as the root mean square quantity. Okay. All right. And then if you do that, your I is equal to V RMS divided by Z, the impedance, right? So you can see this is then is equal to V RMS times I RMS times R over Z, okay? Where we can write R over Z as cosine, okay? A cosine function, cosine of phi. So this cosine of phi is called the power factor. So cosine phi is equal to R over Z, okay? So that's because, maybe let me show you why that's a cosine of that. So because your Z is equal to square root of R squared plus XL minus XC square, okay? So you can imagine if you have a right angle triangle like this is your R, this would be your XL minus XC, then this would be Z, right? Because Pythagorean theory, R squared plus this guy square equal to that, or this Z equal to square root of that, okay? So then the angle phi will be this angle, okay? So if that's the angle phi, then cosine phi will be R over Z, okay? That's the power factor of an RLC circuit, okay? All right, so we can take a quick look on the power factor here. So in this case, it says determine the power factor for an RC circuit with R equal to 4.0 kilo ohms and C equal to 0.35 microfarad that is connected to an AC generator with an RMS voltage of 24 and a frequency of 150. All right. So in this case, you only have R and C, you don't have L. So then your impedance Z as a, this equation tells you it's equal to this gap, but you don't have L in the circuit here. So this is 0, okay? So you don't have a L in the circuit. So that goes to 0. So then your Z is simply square root of R squared plus XC squared, okay? It gives you the R, you can calculate what's your XC. XC will be equal to 1 over 2 pi F times C. Okay, you can calculate that first. So this would be equal to 1 over 2 pi. The frequency given as in this case is 150 Hertz. Your C is 0.35 micro. Okay, so that would be 3.03 times 10 to the third ohms. Okay, for your XC. You're looking for power factor, you're looking for cosine of phi in this case, which is defined as R over Z, all right? Now you need to calculate your Z first because you have R already, but you can calculate your Z. Then you can calculate what's R over Z. So your Z is equal to 3 kilo ohms square plus this guy's square, 3.03 times 10 to the third square, okay? So this would be equal to 5.0 times 10 to the third ohms, okay? Then you can calculate what's R over Z. R over Z is going to be 4.0 times 10 to the third over 5.0 times 10 to the third, okay? That equals to 0.80, okay? So power factor, it's how much power is being consumed, okay? It's a percentage, actually. It's the percentage of how much power will be consumed, okay? So that's 80% or 0.8. Okay, so this guy is, for power factor, is always going to be less or equal to 1. Okay, if you get something greater than 1, then that's not correct. All right. Any questions you guys might have? All right. So next we'll be taking a look on, so if you have a circuit, but you only have L and C in it, right? You don't have the R, you don't have a resistor in it. So then in that sense, energy will be stored in the inductor and the capacitor because those two elements only stores energy. They do not consume energy, all right? So energy stored in the inductor is in a form of the magnetic field. Energy stored in the capacitor is the energy stored in the electric field. Okay, so then in that sense, the energy will not be consumed, but will be just transferred between the magnetic field and electric field. Okay, so when you have maximum energy, all the energy stored in the electric field, then you don't have any energy stored in the magnetic field. The other around, if you have all the energy stored in the magnetic field, then you don't have any energy stored in the electric field. And then you can have anything in between. Okay, part of the energy being in this one, and then part of the energy being in the inductor. Okay, so this is similar to when you have a simple oscillator where if you have maximum kinetic energy, then your potential energy will be 0. On the other way, if you have maximum potential energy, your kinetic energy will be 0. Okay, so then the energy simply just is moving back and forth in the two fields. Okay, you are not consuming any energy. It's similar to the conservation of mechanical energy, where energy is just being moved back and forth in the form of potential energy and kinetic energy. Okay. All right, I think that's the last topic of chapter 23. So we should be able to take a look at least part of chapter 24. Okay, so chapter 24 is kind of summary of what we learned in electricity and then also magnetism. Okay, so it's described in electromagnetic waves. So it was summarized by Maxwell and then in mathematical forms back in 19th centuries. And this is basically what he comes up. So he comes up with those 4 equations. They are in the differential equation forms. But basically, that describe all those equations can describe all the phenomena we just learned over the past a month or so, covering the electricity and magnetism. And then also the light actually is also a form of electromagnetic waves. So like the cell phone signals, it's a electromagnetic wave. The radio signal is also that, and then also the lights is also electromagnetic wave. So then somebody was joking about when God create light, he basically says those 4 equations, okay, in mathematical language. So let there be light. That means that let's have those 4 equations. All right. All right. But basically, those 4 equations describe the electric field lines and magnetic field lines, and then the changing of magnetic field. If you have changing of magnetic field, you have induced an electric field in that sense. And then the other way around actually also is true. If you have changing electric field, you'll have magnetic field generated. Okay. Another result come out of the Maxwell's equation is the speed of light will be determined by the equation. So it's given as speed of light is equal to 1 over square root of mu naught, which is the permeability of vacuum of free space times um, the permittivity of the vacuum epsilon naught. Okay, so that gives you the speed of light. It's almost 300 million meters per second. Okay, it's 299 something, but approximately 3.00 times 10 to the eighth. Okay, meters per second. And later in the 18th or 19th centuries, Hertz proposed that you can actually have electromagnetic wave. So you can actually detect it. So this is how he detected. He pretty much made a device that can give out electromagnetic waves. And then also he made a receiver that can receive that. Okay. So you can send in signals there, and then you can receive the signal. So that's basically what the radio is working, okay, these days. How you can produce electromagnetic waves, okay? So you can have, so this is something you can have. You can have like two charges, and then you can vibrate them, okay? So then they are moving back and forth, back and forth. So then the electric field surrounding those two charges is varying. If you have varying electric field, then you'll have magnetic field generated, okay? And then you have magnetic field generated, then you can actually give out electric field again. So then that's in the sense of going back and forth. So first you generate electric field, and then electric field is changing, so you generate magnetic field. Now the changing magnetic field will generate electric field again, all right, and then electric field will change, generate magnetic field again. So that's similar to if you create a wave, like in a water pond, then wave will propagate outward. Okay, so similar to electromagnetic wave, they will propagate outward from the source. You can also have AC signal here, something like this AC generator. So you generate varying voltage, which means varying electric field. Then varying electric field will give you a magnetic field. And then again, that magnetic field should be varying. It will give out electric field again. So that's how you can also generate the EMF waves. Okay. So for EMF wave, the electric field and magnetic field are varying as a function of sign. Okay, so you can expect that you have peak magnitude of electric field and a sign function and a peak value for the magnetic field with a sign function. Those two are actually the variation of the electric field and magnetic field, they are actually in perpendicular directions, okay? So they are 90 degrees to each other. So if the blue is the electric field in the figure here, then the red would be the magnetic field, okay? Or the other way around. Now, this is the whole spectrum, okay, of ranging from the lower frequency to higher frequency. Okay, radio waves are in the lower frequency range, and then X-rays, gamma rays, they are in the higher frequency range. Okay, the light that we can see is this very small, tiny band over there, and the middle over here. So we cannot see waves in that range. We cannot see waves in that range either. Okay, it's a very tiny piece of it. If you zoom in to see that, you can see the wavelengths, okay, in that that's in that range. That's the range of the wavelengths that we can see. All right. Also, for the so if you go to the X-ray range, so X-ray is produced by if you have an electron in the nuclear that changes orbital, so from a higher energy orbital to a lower energy orbital, so then you will release the light called X-ray, which we actually couldn't see, but you can detect it. Okay, so that's how X-ray will be generate its high energy EMF wave. The energy of the wave is proportional to their frequency. If you have higher frequency, it will have higher energy. Okay. And also you can have X-rays. If an electron hits an atom, then it will give energy to probably one of the electrons in the atom will excite the atom. It will go to a higher energy state, but usually that state is not stable. So then the electron tends back to go back down to a lower orbital state. So then in that sense, it will give out X-ray as well. Okay. This is one of the X-ray image that you can see the pacemaker here in the human body and then the wirings. Okay, so the X-ray has different penetration depths according to different materials. So for metals, it has less. You can see that. Okay. We will be taking a look at the energy stored in an EMF wave. So I think previously we know that for energy stored in an electric field, as the energy density is equal to 1/2 epsilon naught times E squared. And then also for energy stored in a magnetic field, it's also proportional to the field strength square. Okay. So then therefore the total energy in an EMF wave should be coming from the two combination of the energy stored in electric field plus the energy stored in the magnetic field. Okay, so you add those two together, all right, to get this. This is the total energy density of the EMF wave. And if you use a root mean square quantity, then this is what you get. Okay, so you will use the root mean square quantity that will give you average energy stored in the EMF wave. Okay. Now, because there's energy in EMF wave, so then if a light is striking on an object, then there's energy delivered to the object in this case, because light is EMF wave. So energy delivered, you can take a look on the intensity that will be, so it will be equal to the energy divided by the area in the given time period delta t. Delta U is equal to the energy density times the area, okay, and then times the volume of the light striking the object. Okay, so that would be giving you the density. Okay, the energy density times the area, and then times, or actually the energy density times the volume. Volume is calculating by using the area times the c times delta t. Okay, that's the amount of light being striking on the object. Okay. And then also density can be defined as power divided by area. So you can relate those two together. Okay. The U, I equals to U times C. The C is the speed of light. Okay. So if you see letter C, that means the speed of light here in this case. All right, so then intensity equals to U times C is going to be equal to, you pretty much put C in the first term of U and then C also on the second term of the U there, okay? And it's going to be equal to either C times epsilon times E square or equal to C divided by U times B square, okay? I think I forgot to mention for the relationship of B and E, magnetic field and the electric field, they are having this relationship. So magnetic field is equal to electric field by divided by speed of light. Okay. All right, so then in that case, you can do if B0, maximum B should be equal to maximum E divided by C. So then you will have two expressions for the average intensity. Either this guy, if you have all the energy in the form of electric field, or if you have energy, all the energy in the form of the magnetic field, okay, in the lower equation, in the second equation over here. Okay. We'll be just looking at one example here for this chapter. This one says lasers can be constructed that produce an extremely high intensity electromagnetic wave for a brief time called pulse laser. They are used to ignite nuclear fusion, for example. Such a laser may produce an EMF wave with a maximum electric field strength of 1.00 times 10 to the 11. So then this is, so your E maximum, which we call E0 in this case. E0 is 1.0 times 10 to the 11. All right. And let's see. It's asking you what's the maximum magnetic field strength. Okay. Now B field is equal to E field divided by speed of light. So the maximum strength of the magnetic field should be equal to maximum strength of the E divided by C. So you can calculate that way. So this will be 1.0 times 10 to the 11 voltage per meter divided by 3.0 times 10 to the 8th meters per second. That gives you about 3.3 times 10 to the second Tesla. That's your maximum magnetic field that's possible. This part B is asking you what's the average intensity of the beam. Okay. So average intensity of the beam is equal to C epsilon naught times E square. Okay. So then average, I average. So the maximum intensity then will be epsilon 0 times E maximum square. So average will be equal to 1/2 of the maximum. Okay. C epsilon 0 times E0 square. You can calculate that will be 1/2. C is 3.0 times 10 to the 8th meters per second. Epsilon naught is 8.85 times 10 to the minus 12. And then E maximum is 1.0 times 10 to the 11 squared. So your average is equal to 1.33 times 10 to the 19 watts per meter square. Okay. The last part is asking you what energy does it deliver to an 1.00 meter a millimeter square area. So then on this energy delivered will be equal to the energy density, the average energy density, okay, times the area that's given times delta T, okay. And I think we have the I average, we have the area. Let's see if we have the, yeah, the delta T will be the 1.00 nanoseconds given there, okay. So we can calculate that. 1.33 times 10 to the 19 times the area 1.00 times 10 to the minus 6 meters square. Okay, so this is from millimeter square to meter square. And then 1.00 times 10 to the minus 9 second, the nanoseconds. So it's 13.3 kilojoules times 10 to the third joules. Okay, so that's a lot of energy being delivered to a small area. All right. Any questions you guys might have? Okay. So if not, then we'll stop here for today.